Okay, in this video, we're going to talk about numerical summary measures for the sample. Now, I would expect that most, if not all, of these numerical summary measures are you've seen before. And that's okay. We have to start somewhere in this particular course. What I recommend that you do is you concentrate on the R aspects and also concentrate on trying to get a better understanding of some of these numerical summary measures, especially ones dealing with variability. Okay, so why are numerical summary measures of the sample important? And it comes down to, again, this diagram that we've seen earlier. Again, we have this population where we have a lot of items in it, and we want to better understand it. And we're going to calculate some numerical summary measures of the population itself. And these numerical summary measures are called parameters. And so what we do is, since getting at all the items in the population is so difficult, is that we go into the population and we take out a representative sample. And the sample is going to be a smaller set of items or objects that we can work with and calculate numerical summary measures of those items in the sample. These numerical summary measures are called statistics. And so what we then do is we want to use these statistics to infer back to the population about what the corresponding parameter values are, so we can make judgments about what's going on in that population. So in this section, we'll talk about statistics, but we also will talk about the parameters that we're estimating. Okay, so let's start with some measures of centrality. In other words, if we have a particular variable of interest and we have some observed values of that variable, where is essentially the center of all those values? And one measure is essentially the mean, or the average value. So we've discussed the population mean before. It's simply the average of all the values in our population. We use the Greek letter mu to denote this population mean. But let's suppose that we take a sample from this population. The sample is the size of n, and we get particular observations. Again, we are observing values of our particular variable of interest on items that have been essentially sampled from the population. So if we think back in terms of the GPA example, the first value that we get is going to be denoted in a generic manner as Y1, and maybe that was 3.0. The second value that we get in our sample is going to be denoted by Y2. Maybe that was 3.1. And if we just want to be very general, the nth value that we got, maybe it was 2.8, and so on. So the reason why we use letters there, even though I did write out numbers, is it provides a general way to represent the values of our observations that we have, so we can talk about more than just simply the GPA problem. So using these y's, then we can come up with the sample mean, or the average of all these sample values. We denote this average by y bar. So again, we actually pronounce it as y bar. And what all that y bar is we take the first sample value plus the second sample value plus down to the nth sample value, and we divide by the total number of sample values so that we can get an average. In a more compact way, more general way to write this, we can use some summation notation that you would learn about first in like an algebra class. And so we take the sum from I equal 1 to n of y sub I, divide by n. That's our y bar. Again, the purpose of y bar is to estimate mu. Now, another measure of centrality with respect to a particular variable in the observed values is the median. And all that the median is the actual center of the data values when they are arranged from smallest to largest. Now, because you might have an odd number or an even number of these values, this median can, you have to have different expressions for them. So if, let's say, if n was odd, then we simply take the n plus 1 divided by 2 ordered value. If n is even, well, find the n divided by 2 value, find the n divided by 2 plus 1 value, and take their average. Okay, so let's look at a simple problem just to make sure that we can do these calculations. My corresponding R code is in the program simple_gpa.r. So let's say for some reason we have this very small population consisting of, I think, let's see, that's about 10 different values. And since we can write them all out, we're able to calculate the population mean of 3.01. Okay, again, this is a simple example. That's why you see the word simple there. Anyway, suppose though we take a random sample of size 4 from this population. So perhaps the first time that we sampled one item, we got 2.9. So it's this one right there. The second sampled value was 3.4. The third one was 3.6. And the fourth one was 2.8. And if you average those, simply you get 3.175. Now note that this is not exactly equal to the population mean. In fact, it's off by about 0.165. So it's fairly close, but it's not exactly. We wouldn't expect it to be exactly equal to the population mean. Well, what if we took another sample though? Same size, 4. And maybe we got 3.6, 4.0, 2.7, and 2.8 in this sample. Well, that sample average, or sample mean, is 3.275, and we're off by 0.265. So again, sample mean is not equal to the population mean. Rather, it provides an estimate. And so, we could keep on taking many more samples. And very rarely, if any of them, will actually be equal to the population mean. But what we like to be able to do, and this is one of the main purposes of this course, is to have some measure of how good is this sample estimate that we got, this sample mean in this particular case. Also, in order to make that judgment, what we're going to do is try to quantify this variability that we see from one sample to the next sample. And that will be done later in our course. That will help us then to get some kind of a measure of how accurate our estimate of the population mean is. Well, what about the median then? Well, again, if we go back to our original sample, we ordered them from smallest to largest. We have an even number of items here. So based upon what I mentioned a few pages before, excuse me, we take the average of the n divided by 2 value and also the n divided by 2 plus 1 value. So in other words, the second and the third values here, we take that average and that becomes our median, in this case 3.15. Suppose though we added another observation that was greater than 3.6 to our data set, maybe it was 3.8. In that case now we have an odd number of items and simply the median would be that middle value after you order them, it would be 3.4. Well, how do we do these calculations in R? Let me come on over here to 10 again. So I'm going to create an object called Y. It's going to consist of the combination or the concatenation of 2.9, 3.4, 3.6, and 2.8. Okay? So let me just go ahead and run that. Oops. Let me try that again. And so we can see that Y is indeed the correct value. We can use the mean function that we've seen before to calculate this mean is 3.175. And the median function calculates, as you might expect, the median. Let me come back here. Now there are other ways to calculate these measures. For example, we've also seen the summary function too, and that would work. So we have the mean, we have the median. which is a better measure of centrality? Well, the median ends up being a little bit more in what we say in statistics robust to extreme values, also known as outliers. So if you have some very large values in your sample, the median is not going to change as much as the mean would. And so to some respect, the median is actually a better estimate. In the end, though, we often work more with the mean because it has some nicer mathematical properties to it. What I would like you to do, though, is I want you to think about why is the median not affected by extreme values as much as the mean. So one way to do that is just to, let's say, create your own small data set, maybe of 10 values. So you took a sample, you got 10 different values. And look what happens if you change one value in the data set and make it more extreme, more farther from the center of all those data values. Look what happens. What happens to the mean? What happens to the median? Do that for a number of different times, and then you'll be able to answer why. And who knows, maybe you'll get to answer why again in the future, such as on a test. So let's talk about some measures of variation. In other words, I want to know how these items vary through the data set. Are these observed values, that is, are these observed values, do they tend to be far apart, or are they close together? So one simple measure of variation is the range. And simply, it's the maximum value minus the minimum value. So for example, let's say if I had a sample consisting of the number 100, 10, 11, and 9, well, the range is 100 minus 9. The maximum minus the minimum, you get 91. Now, as you can see here, this 100 is kind of different from those other numbers. And it also helps you see that a range is very sensitive to outliers, or these extreme values. And so because of that, we rarely will use the range to measure variation. Instead, what we will do is typically use something called the variance. And in fact, this is probably one of the most important measures in statistics. Depending upon your background before coming into this course, you might be thinking, okay, what statistics is? Well, we calculate some means, we calculate some medians, maybe some percentiles and stuff. But actually, statistics is most concerned about this variation. How do we measure it? How do we find things that account for variability? So for example, this is an example that we'll get to later too. Let's say you're interested in the amount of time it takes you to get to class every day. Maybe one day it took you 9 minutes, another day 4 minutes, another day 12 minutes, another day 8 minutes, and so on. In statistics, we're very interested in the variability of these numbers. How are they dispersed? And in fact, we will be very interested in why on some days would it only take you 4 minutes, but on other days it would take you 12 minutes. We like to be able to explain that variation. And you'll see many examples of that throughout this course. And if you take more statistics courses, you'll see that as well. Okay, so let's first talk about this variance in terms of the sample. And all that it is it's a measure of the average squared deviation of the observations from their sample mean. In other words, we're going to first of all denote the sample variance as S squared. What we do is we take the first sample value and we subtract off the overall mean of all those sample values and we square it. So notice what we get here. How far is Y1 from the center, the mean? And we square it so that we're always dealing with positive values. More on that shortly. Then we look at the second value. We compare it to the mean, square it. And we keep on going down to, let's say, the nth sample value. Compare it to the mean, square it. And then we would like an average of all those values. What is the average squared deviation that we have here. And you might be thinking, well, okay, average value, divide by n. Well, instead we actually divide by n minus 1. Because in the end, this s squared is going to be a better estimate than its corresponding measure in the population variance. In a more compact form, we can again use our summation notation. Take the sum from I equal 1 to n of yi minus y bar squared, and you get what I had just written on the other side. Then the population variance is the same measure essentially, but now we look at all the values in the population. Suppose maybe there are capital N different of these values in the population. And since we're dealing with the population, let's subtract off mu from the y's instead this time. And again, as a measure of the overall average variation, we now divide by just capital N. Okay? So let's look at some questions and some comments that I have here. Let me get to the right spot on the notes in my paper copy. So we're on page 7. So s squared estimates sigma squared, just like y bar estimates mu. So we have already talked about the second comment here. Let's talk about the third one. What characteristics of the sample will lead to a very small s squared? What characteristics of the sample will lead to a very large s squared? Well, that's a good question, or a good set of questions, to help you get an intuitive understanding of what this measure is. So think of it this way. When would s squared be 0? Well, it would be 0 if all the y's were equal to y bar. So that square deviation would always be 0. Now, if the y's are a little bit different from y bar, now this s squared is going to be a little bit higher than 0. If instead these y's were really far apart from each other, these square deviations are going to be large, and therefore the s squared will be large. So, then to answer the question then, s squared is going to be small if the y's are close to the sample mean. In other words, the observed values are always very close to essentially the middle of the data set, or middle of the data, center of the data. S squared is going to be large if there's a lot of differences amongst these items in terms of their numerical values that we're sampling. So they're quite dispersed. That's when S squared is going to be large. So why then, so another question, why do we have the square in this yi minus y bar part? Well, if I did not have the square, so let me just write it out like this instead of going back in the notes. This will always be 0. You could do a mathematical proof to show that. Instead, what I recommend that you do, or I would like you to do, I should say, is actually try it on your own for a data set. It could be a very small data set. Subtract off the mean of all the sampled values every single time, and you'll see that these deviations here, no longer squared, end up adding up to 0. So another measure of variation, though, that you do not see as often is that you could use a absolute value instead. Now this numerator no longer will add up to 0 because, of course, absolute values are always greater than 0. And so that would be another one that you could use. And you'll see that used in some places in other kinds of problems. But by using the square here, we have some nicer mathematical properties again. So that's why we typically use that instead. Okay, let me do some erasing here. Okay, let's look at the next bullet. Suppose you had two samples consisting of the following numerical values, 8, 9, and 10, and then also 7, 8, 10. Without going through the calculations, which sample would have a larger s squared? So again, think about what S squared measures. It measures how much variability are there in your observed values. And if you just look at those data values, you should be able to see, well, which one, the first set or the second set, has more variability without actually even doing the calculations. So I do want you to do that on your own. Then let's say that the 10 in sample 1 was changed to 11. So maybe this was 11 now. Which sample would have now the larger S squared? Maybe neither of them. Maybe they're the same. Now, again, to get an intuitive understanding what variability is, you need to think about, well, why is that? Because in this particular case, the mean is going to be different for sample 1 and also for sample 2. But in the end, you will have the same variance. Because all we're measuring is how far are we from that centered value. And whether you have 8, 9, and 11, or maybe you have 80, 81, and 83, or you keep on going, the differences amongst them is still the same. Excuse me. Now there is one problem with this variance measure, and that is, since we are using a square there, we're actually measuring everything in squared units. So perhaps, let's say yi is a length, let's say in inches for something, okay? So since we're working with yi minus y bar squared, now this variance is actually inches squared. And that can be a little bit more of a difficult thing to interpret. So because of that, very often, rather than working with the variance directly, we work with its positive square root, which is known as the standard deviation. Since we're taking the square root, we are no longer in squared units. Now we're in the original units of the data. So the sample standard deviation, we're going to simply denote it as S, is the positive square root of S squared. The population standard deviation is going to be denoted as sigma. It's the positive square root of sigma squared. So let's take a look at another example. This is a simple GPA problem again. Let's simply calculate this sample variance. Let me actually get what the original sample values were. Hold on a second. So I'm just going to copy and paste it. Okay. So what we need to do is, we know the mean already is 3.175. So we simply take the first sample value, we subtract off the mean, so this is y1 minus y bar, we square it. We do that for all the sample values. Our last one is y4. We take the sample value, subtract from the mean, square it, add them up, divide by 4 minus 1, or 3, and we get 0.1492 as the sample variance. Do note that I like to, on a test, often give a small problem for a small set of observed values, where I actually have students calculate the variance essentially by hand to show that indeed that they can work with that mathematical expression for it. So the sample standard deviation then is a positive square root of 0.1492 or 0.3862. One could calculate the population variance as well, and we get 0.6109. Population standard deviation is 0.7816. Now again, remember, S squared estimates sigma squared, or equivalently S estimates sigma. And so we can see that we were somewhat off. So the true standard deviations, or the population standard deviation, is 0.78, but we got 0.38 for our sample. Okay, So let's talk about how we can do this in R real quickly. Simply, there's a var function, there's an SD function that does the calculations for you. Pretty simple. Okay. Now, when people ask you to interpret a mean, well, that's easy. Average value. It's like a measure of centrality. And if someone tells you the mean GPA is 3.0, you have a really good understanding of what that means. But if someone says instead that the sample variance of the GPAs is 2, or that's actually not 2, how about 0.2? Do you really have a good understanding of what that means relative to the actual data values? Most people don't. And so the purpose of this next part here is to help give you this intuitive understanding of what variance, what standard deviation means then relative to your actual data values. And I call this the rule of thumb for the number of standard deviations that all data lies from its mean. That rule says that most data values, observed values from your data set, should be 2 to 3 standard deviations from the mean. In other words, take y bar minus 2 times s and take y bar plus 2 times s. And do the same thing with 3. So, why is this useful to know? Well, let's get back to this example that we talked about earlier with respect to the amount of time it takes you to get to class every day. Let me go to R for this too. Let's say I'm going to put this into a vector y. Suppose the first day it took you 4 minutes, the next day it took you 9 minutes, the next day it took you 8 minutes, and the next day it took you, let's say 7 minutes to get to class. And so here's my y, and let's calculate the standard deviation, 2.16. Okay. Now what the rule of thumb says is if you take the mean of y, subtract off 2 times that standard deviation, you get basically a bottom value or lower value that you would expect all your data values to fall within. In this case, 2.7 about. Now we can also do the same thing with a plus in there, 11.32. So what this says then is that, as long as, the conditions of you coming to class every day don't change, generally speaking, it should take you between, let's say, 2.7 and 11.3 minutes every time to get to class, generally speaking. And so then you can put this into practice in terms of, well, what time should you leave, let's say if you're coming from home, what time should you leave for class every day? And how about, just to be safe, to make sure you get to class on time, how about 12 minutes before class starts? And so that's how this rule of thumb can actually be used in practice. Well, where does this rule of thumb come from then? Well, actually it comes from 2 other rules. The first one is Chebyshev's rule. I think Chebyshev, if I remember right, was a Russian mathematician a long time ago, and sometimes you'll see different spellings of his name. And what Chebyshev's rule says is that at least 75% of all observations should be within 2 standard deviations from the mean. And at least 89% of all observations, and this is actually no matter what, should be within 3 standard deviations from the mean. And we can also look at another rule called the empirical rule. And that says that approximately 95% of all observations are within 2 standard deviations from the mean. And approximately 99.7% of all observations are within 3 standard deviations from the mean. Wow, that's quite an increase here from what we had with Chebyshev's rule. Well, in order to get that increase, though, you have to make certain additional conditions. They need to hold true. We'll talk about that a little bit more later. But basically, the main thing right now to understand is that this is where this rule of thumb essentially comes from kind of a combination of these 2 different rules. So let's take a look at an example in R. This involves wind speed in Lincoln, Nebraska. And what I did a few years ago was I found a cool weather website that gave me the average daily wind speeds for every day in February over a 5-year period. And obviously wind changes throughout the day, so let's not worry about the fact that this is an average value. Let's just say this was the wind speed. And so I have this data over, again, 5 years. And so one might be interested in then is, well, why would someone be interested in something like this? Who cares about the wind speed? Is it because now you're worried that when you walk to campus every day, if it's too windy, your hair might get messed up? I guess that might be one reason why someone would be interested in this. But really, I think the main interest, especially nowadays, is with respect to wind power. Utility companies need to understand how windy certain locations are to decide if they're going to put a wind farm up. And they need to then use the information about average wind speed in those locations to get a judgment of, well, how much electricity will be generated from this wind farm. So the second question is, well, what's the population? Well, I would say, well, the population is essentially, let's say, all Februaries. But of course, now we have some problems because we have just 5 months or 5 years worth of data here, especially with, conditions like global warming and stuff like that. The wind could change over time. So we have to, the population is not maybe as well defined as maybe we would like. But let's say for the near future, that's our population, what we've sampled and in the future. Well, what's a random sample? Well, first of all, is this a random sample? And the answer is no. We've collected 5 years worth of data. These are actually 5 consecutive years. So no, it's not a random sample here. So any kind of inferences that we want to make, let's say from the sample to the population, you got to be careful. What you're basically saying is that these 5 years are truly representative of what will be happening in the future. And overall, what we see here is basically what you could say is an observational study, because we are not necessarily controlling other items that may be related to wind speed here. This is in contrast to a scientific study where we would actually try to control these additional items here. We will have many more examples of understanding what observational and scientific study are as we go along in this course. So in total in this data set, we have 142 observed values. And so let's take a look at this. Let me come over here to the wind speed example. So the data is actually in a comma delimited file. Again, you can download that from my website. And what I'm going to do is read it in using the read.csv file, put it into an object called wind. I've already done that. And if we wanted just to take, let's say, a look at the data to make sure that indeed it did work. Whoops. Let's do that. Here's all my data. That's a lot of data to look at. So especially as you get larger data sets, it's often better to, if you want to check to make sure you read in the data correctly into R, is you use a function like head. And what head gives you by default is the first 6 observations. And from what I see here, if I go back to the actual data set itself, then indeed I did read it in correctly. Let's see here. So with this head, again, you get the first 6 observations by default. You can change that by using the n argument. So let's say if I want the first 10, I use n equal 10. There's also a function called tail, which gives you the bottom 6 observations by default in the data set. Do note that wind here is actually, in R's terminology, a data frame. Okay, get to the right spot of my printed notes. So let's do some summary measures. Let's calculate the mean of wind. Of all the winds. So notice the winds are in a variable called y. And so on average, the wind speed was 10.2, and this is in miles per hour. Well, what would be another way that we could write it or calculate this? Well, remember what the mean is. It represents the sum of all the observed values divided by the total number of observed values. In R, there's a function called sum. So if I use sum with the y values in win, I get 1,448.4. If I want to take the average of it, I need to somehow calculate, well, what was my overall sample size? And so in other words, if I take a look at win $y again, what I like to do is somehow maybe come up with a way to count all these items automatically. In other words, how long is this sequence of numbers here? And so if I can do length, I can spell it right, win $y, and I get 142. And I just want to go back and mention one thing too, since we're new with using R here. Again, wind is a data frame, and if I use the names function with wind, we see that we have 3 components to this data frame: year, day, and y. Y is this wind speed. And in order to access particular values in this data frame, I can do win $y, and I get all the y values, all the wind speeds. Alternatively, I could have done this: win left bracket, comma 3, end bracket, excuse me, and I get the third column of all those data values. What you should do on your own is ask yourself, suppose that I did win bracket 1, comma, end bracket. What will I get? Think about it. Okay, so when I combine sum, the sum function, with the length function, I get my mean again. So let's take a look at the median. So the median is a little bit less, 9.7 miles per hour. Okay, so let's take a look at how we can do these calculations now for a standard deviation. So in most situations, what you would do is simply use the SD function that we've seen before, and you get 4.47. Well, let's show that we can actually work with the corresponding formula that we have seen a few minutes ago. And so what we would need to do is take our wind speeds, which are in y, subtract off the mean of the wind speeds. And so we get all these deviations from the mean. So remember that the mean for wind $y is 10.2. And the first data value is 9.4. So if I take 9.4 minus, 10.2, I get negative 0.8. And so we've seen some of this before, this behavior of R, in the introduction to R notes, where what R does is actually does essentially an element by element subtraction in this case. Y here has 142 values in it, and the mean of Y has just one value in it. And the way that R behaves, it actually takes every single one of those 142 values and subtracts off the mean. Okay. Now with the standard deviation formula, we need some squared deviations from the mean. So that negative 0.8 before that we had now becomes positive 0.64. Also with the standard deviation formula, we need the sum of these squared deviations. We saw how to use the sum function before, and there's the result that we get. And essentially then we need to get like an average value. So let's divide by n minus 1. And then lastly, let's take the square root to get the standard deviation. Now I went through this little exercise here to show you how nice R can be to work with, so that you can understand how these calculations are done. In the program itself, I essentially went immediately to the long expression that I had at the end. But what you can do is actually highlight part of the code inside of it and run that and see what happens. So let me just do that. Oops. And there's those deviations from the mean again. Okay, now that we have the standard deviation, let's now come up with this rule, or let's apply this rule of thumb so we can get a more practical idea of what the standard deviation means relative to our data. So to do that, I'm going to copy some stuff out first. What I need to do is take the mean, subtract off 2 times that standard deviation. We'll also do the mean plus 2 times that standard deviation. And so I get 1.24 to 19.15. Excuse me. So what that tells us is that pretty much all the data values in our data set should be between these two numbers. And we'll look at shortly if that actually does occur. Now, another way that I could have done these calculations is, or actually put the resulting calculations, is put them in a data frame. And to create a data frame, you can use the data.frame function directly. So if I say data.frame, where the first variable is going to be the lower limit, notice I'm going to have that calculation that has the minus in it. My second column, my data frame, is going to be the upper limit. So notice I put a plus there. And again, I'm working with 2 standard deviations. How about we do the same thing with 3 standard deviations as well? And this is what we get. Same as what we just saw. Okay. Now, if I wanted to, I could have saved those results from that data frame into an object. Again, you can do that with any calculation that you do. So how about if I create an object called save.interval? It's going to get the results from data frame. And if I want to, I can just I can actually, first of all, use names, save.interval. Oops, wrong way. There we go. Let's try that again. There we go. So we see the lower and upper values. And so I could then just pull out the lower value as well, and I get 1.24. Okay. So we are on page 12 of the notes. Let's look at, well, how many actual values are outside of this range that we got. I mean, again, the rule of thumb says pretty much all should be within 2 or maybe 3 standard deviations. Let's actually calculate how many are. So what I can do is do like a logical comparison. Let me get a drink of water again first. And so we can take a look at all the wind values, all the y values in the wind data frame, and look at, are they greater than that upper value? And so I'm just going to highlight that segment of code and run it. And notice what we get, a bunch of trues and falses. So we can see, for example, let's see now. So this, well, actually look at this one here. So 133, 134, 135, 136, 137, 138, the 138th value is actually greater than that upper limit. So let's actually look at that. 21.6. Indeed, that is larger than 19.15 that we had calculated. And so we have all these trues and falses. And what you can do is actually add the trues and falses, and that might seem odd, but what R does, it takes a true to be a 1 and a false to be 0. So if I do that, we see that there were a total of 6 different trues. So 6 times out of 142 is the number of times that we were outside this upper limit. So 6 divided by 142 is, well, about 4% of the time, not much. In terms of the lower value, how many times are we less than it? Oops. 0. So we can see indeed that this rule of thumb does hold with respect to this data. Pretty much all the data values are within 2 standard deviations of the mean. So that's really cool. And so if we go to page 13 then, the question then is, well, why would this be of interest? Well, again, think of it from a wind power situation. a utility company would like to know, essentially where should most of the winds be, or what should the wind speeds be most of the time. And essentially, this rule of thumb kind of gets at that, answering that kind of a question. Okay, let's next take a look at a new example. This example deals with what I call the serial data set. We'll look at this example a number of times in our course. The corresponding stuff that I do is in serial.r in terms of the R programming, and the data is in a comma delimited file, serial.csv. So with respect to this serial data, I've always been curious about how grocery stores decide to do shelf placement for their corresponding cereal boxes. Why is one type of cereal typically found maybe on a bottom shelf, while another type of cereal is typically found on a top shelf? And to help motivate why I was interested in that, I have a short video of my son Callum, who I turned loose in the cereal aisle one day. Callum's a little bit older now, but in this video, I think you'll get an idea of why perhaps grocery stores put certain kinds of cereals on particular shelves in a cereal aisle of a grocery store. So let's quickly take a look at it. So notice he picks up
we'll put them in here.
Crisp. This is a very high sugar content cereal that's marketed towards little kids. And then next
that's
is
like healthy.
Puffs. Again, another high in sugar content cereal. And guess what? He even picks up another one and puts it into our shopping cart. And so, based upon what I observed with my young children, including Callum here, it appeared to me that perhaps those cereals that are marketed towards kids typically tend to be on the lower shelves because these kids are shorter. They can't reach up to the top shelves to pick up the cereal and put it into their parents' cart. Instead, what they can do is they can do the bottom shelf, let's call that shelf 1, or maybe even shelf 2 as well, the next one up, and they can grab those cereals and put them into their parents' cart. And then of course, the kids hope that the parents will actually buy those particular cereals. And so what I decided to do was I went to a grocery store and I took a stratified random sample of the cereals that were in the cereal aisle. And typically the way that these aisles are constructed in stores is that, let's say, one whole side of the aisle in terms of the shelves is all with cereal. And in this particular store, there were 4 shelves of cereal. Shelf 1 is going to be the bottom, shelf 4 is going to be the top. And in terms of taking a stratified random sample here, what I decided to do was I picked a strata, which was shelf, and within that strata, I randomly selected 10 different cereals. That way I could get a good representation, or at least I hope I could get a good representation of what was on each shelf in the cereal aisle. So for example, shelf 1, the very first cereal that I chose in my random sample was a Kellogg's Razzle Dazzle Rice Krispies. It had a serving size of 28 grams. And because I know that, unfortunately, typically the high sugar content cereals are typically marketed towards kids, I decided to record, well, how much sugar content was in the serving size. In this case, it was 10. So more than 1/3 of the serving size basically was sugar. And since I was recording sugar, I thought I could also record fat, and I could also record the sodium, which is in actually milligrams. So that was the first cereal that I selected. The next one is Post Toasties Corn Flakes, and so on. So when I went to shelf 2, the first item that I randomly selected was Rice Krispies Treats. 30 grams was the serving size, 9 grams of sugar for that serving size. Now, if you notice here too, that each of these serving sizes, or most of these serving sizes, are actually different. And very shortly, we're going to have to take that into account in our analysis. Okay. So, some questions. I want you to think about on your own, well, what would be the actual population here that I'm sampling from? Is it just this particular grocery store? Is it maybe all grocery stores? Or maybe is it a particular grocery store brand in terms of all their corresponding grocery stores? And then think about, depending upon what your answer is, think about, well, could all the population values actually be obtained? So if you have any questions regarding these questions, you need to ask. In terms of like a message board or during some kind of class setting. Okay. So the data is in a comma delimited file. It's called serial.csv. So I read in the data into R. I put into an object called serial. Let me go ahead and go over here to R. And what I do, first of all, is I make sure that I read the data incorrectly. So I use the head function with it. And indeed, based upon, if I went and actually showed you what the file looked like, indeed, it does look like I did read the data incorrectly. Okay. So next, let's take into account that these serving sizes are different for most of the cereals. You know, wouldn't it be fair to compare, let's say, one cereal that had a serving size of 1 gram to another cereal that had a serving size of 30 grams? You know, that 30-gram cereal, in terms of the serving size, might have more sugar content just simply because it's a larger serving size. So to take that into account, then what I'm going to do is I'm going to take the sugar values and then divide it by the serving size, simply put. And we'll also do that for fat. We'll also do that for sodium as well. Do note, though, that sodium, again, is measured in milligrams. And so once I do that, I want to be able to save these results. And what I'm going to do is put these new, let's say, variables back into my original data set. And the way that I do that is I create a variable called sugar in the serial data. So if sugar actually existed itself in the data set itself, I could just call it serial $sugar, but it doesn't. Instead, I am going to do this adjustment to my data and put that adjustment into my original data. And then we'll look at the head function with serial to see, indeed, is it actually in there? Okay, so if you remember, that first cereal had 10 grams of sugar for a serving size of 28. So 10 divided by 28 is 0.357. And look at this, we have a new variable in our data set, and that first value for that first cereal is indeed 0.357. So it appears that this has worked. Okay. So let's see, we are now on page 16 of the notes. Let's do some summary measures of this data. Now, what I could do is this. So cereal, $sugar, that's going to now give me, again, all the different sugars. And I know the first 10 values are shelf 1. And if I want to find, let's say, the mean value of just shelf 1, I could use the mean function with this. Again, as a reminder here, the colon in R represents the word 2. So 1, 2, 10, 2 as in TO. This will give me the first 10 values. And then I can use the mean function with that to see the average sugar content, or the mean sugar content is 0.2568. And then I could go ahead and do that for the next shelf as well. Remember, there's 10 cereals per shelf. That's why I'm going by 10 here, and I get 0.41. But there's actually an easier way to do this. There's a function R called aggregate. Its first argument basically says, well, how do you want to aggregate or summarize the information that's in your data set? And I'm going to use the formula argument where I want to aggregate all the sugar values, and I'm going to do it by shelf. And this is just a kind of a syntax here to separate the variable that you're interested in and essentially the by variable. Use a tilde. My data set or data frame is cereal, and how do I want to summarize all the variable values? Well, I want to have some fun, and I want to summarize them by the mean. So fun corresponds to function. So if I go ahead and do that, we can see that now I have the mean values by shelf. And let's take a look at the results. So we can see like shelf 1, shelf 3, and shelf 4, its sugar contents, at least on average, are about the same. But look at shelf 2, 0.41. So it is pretty much higher, or pretty higher. And again, if we go back to this video with Callum, you can see that, look at where his head is. His head is basically right at shelf 2, and those are the cereals that he is, or at least the last 2 cereals, that he's actually picking out and putting into our grocery cart. Now, we could also do some other summaries. We could, for example, use the standard deviation as well. And we can see here that we do see some differences amongst the standard deviations where, interestingly, shelf 2 has the smallest standard deviation of all the shelves. Maybe this represents that those particular cereals are more homogeneous. Maybe perhaps, and this is, we're just doing some initial investigations here, maybe it's perhaps that they tend to all be these children's cereals that are high in sugar content. Okay. So that takes us to page 17 then. So what have we learned about the sugar content of these cereals and their shelf placement? Well, it appears that there might be some kind of trends here, that indeed shelf 2, which is the second to lowest shelf, might have tend to have some higher sugar content cereals. Now, this is by no means a formal analysis. We will actually more formally look at this later in the course when we start talking about inferences, but this is our initial investigation into the data here. Okay, so let's move on. So we've talked about the mean, we've talked about measures of variability, the variance and the standard deviation. I guess we've also talked about the median as well. Excuse me. Now let's also talk about measures of position, like a percentile. So for example, the pth percentile is the numerical value where at least p% of the items are less than or equal to this value, and also 100 minus p% of the items are greater than this value. So for example, maybe I might have a 75th percentile. That means 75% are lower, 25% are higher. I would assume that all of you have seen percentiles before. Often one of the first places where you see these percentiles is with standardized testing, like in an elementary school setting, or even going into college, where you're given a percentile rank of how you scored on a particular exam. Now, perhaps you don't know this, but, or actually, I expect most of you don't know this. There are actually many, many different ways to calculate a percentile, despite the concept being very, or relatively simple. R actually has 9 different ways. And I don't want you to worry about the different ways too much. There's small advantages over one over the other in particular situations. I don't really think it's worth our time getting into, but let's just take a look at one particular method. And to find percentiles, what we do is we order the data values from smallest to largest, and then the jth ordered observation corresponds to the 100 times j minus 0.5 divided by n percentile, where n is our sample size. So simply, if I had a sample size of 20, this first observation that we have in our sample, so that's what our j is going to be, ends up being the 2.5th percentile. The second one is the 7.5 percentile, and so on. Well, what about though if you wanted the 5th percentile instead, rather than the 2.5 or 7.5? Well, in a sample size of 20, there is not necessarily one answer for what that would be. And this is where a lot of different methods have evolved about how do you find something in between. One simple way would be to use what's called linear interpolation. Don't worry, I'm not going to ask you to ever do that on a test or anything. In this particular case, since 5 is halfway between 2.5 and 7.5, what you could simply do is take the average of these two percentiles, 2.5 and 7.5 percentile, those corresponding values, and there's your 5th. So we've talked about percentiles. Something that's maybe less talked about in other situations is what's called a quantile. In statistics, actually, we do mention quantiles a lot, and so it's important you understand what the differences are between a quantile and percentile. And actually, it's just a small difference, but you need to make sure you use the correct terminology. So, for example, the 100 times Q percent of the items that are less than or equal to this value, and 100 minus 100 times Q percent of the items are greater than or equal to this item value. This would be the Qth percentile. In other words, the 95th percentile is the 0.95 quantile. I guess that's a lot easier way to say it, and perhaps I should just start it off with that. Now, some important percentiles and quantiles. So the median that we've seen before is the 50th percentile, which would be also called the 0.5 quantile. Some people decide to add even more terminology, and they often refer to this as Q2. I won't do that myself. The 25th percentile, or in other words, the 0.25 quantile, is often denoted as Q1 by some people. Some people even call that the first quartile. And there's something similar that happens with the 75th percentile as well. In our class, I'll just focus on percentile and quantile, just to make things easier. So let's take a look at an example. This deals with cholesterol levels. Let's actually go over here to 10. Okay, so this data comes from Ott and Longnecker on page 93 of their 7th edition. And the Y values are going to be cholesterol levels. And it just so happens I've already ordered them for us, and so I've read them into an object called Y. If they were not ordered already, then you could just simply use the sort function to actually order them. Just to show you again how you could work now with a data frame, I could create a data frame using the data.frame function, and I put the Y's values there. If I wanted to, I could just simply use that segment of code, and the variable will be called Y in the data frame, or I could name it something different by saying the new name equal than what the actual vector of information is. I'm going to put that into an object called set1 and use head of set1 just to check it out, and indeed it does look like what we had previously. Okay, so now we're on page 20. So let's talk about how to find percentiles and quantiles in R. There is a function called quantile that will allow you to do both. So if I say quantile, and then the first argument happens to be just generically called X, and what I want to do is I want to pull Y out of set1. And what quantiles do I want to get at? And that's where the argument probs for probabilities is used. And what I would like to find is a sequence of quantiles corresponding to 0.025 to 0.975 by 0.05. And as I mentioned before, there are actually 9 different ways that you can actually find a quantile or percentile in R. We're just simply going to use type equal 1 here. And if I go ahead and run that, put the results into type 1, here we go. So the 2.5 quantile, or I'm sorry, the 0.025 quantile is 133. The 0.075 quantile is 137, and so on. Okay. Now, the way that I described how to find percentiles and quantiles earlier actually ends up having to correspond to type 5, or type equal 5. And so if we take a look at that, you'll notice we get exactly the same answer as what we got using this type equal 1. Just use type equal 5 all the time. For our course, that will be just simpler. Do note the default happens to be type equal 7. Well, let's take a look at how these values differ amongst the different types. We can see type 1, type 5, as I said before, are exactly the same, but we can see that indeed that you could get differences, different values. And so type 7 does give you slightly different values throughout here. So where you often see more differences amongst quantiles and percentiles is, if you have a set of 20 different data values, is what we do here in terms of these cholesterol levels, is if you look between the 2.5 and 7.5 percentiles, you'll see where differences occur. So let's go ahead and do that with type equal 5 and type equal 1. And we can see that, and notice how I'm doing a sequence of numbers from 0.025 to 0.025 by 0.01. We can see that indeed we do get some different values. Again, just use type equal 5. That will work for what we're going to do in this course. I mentioned these other percentiles and quantiles just to show you that indeed there are other ways to do the calculations. They end up being, generally speaking, just about the same across all the different methods. It's really not worth our time to get into a discussion about why is one method maybe better than another in a particular situation. For what we're doing here, type equal 5 will work just fine. Okay. So lastly then, this is on page 21. Well, suppose you're in a situation with this wind speed data set. You're working for a power company, utility company, and suppose a power company needs to know whether the wind speed is greater than 5 miles per hour at least 80% of the time. They need to know that in order to decide if they want to put a wind turbine in a particular location. And so to be greater than 5%, greater than 5 miles per hour, at least 80% of the time, what you're doing is you're looking for the 0.2 quantile then, or the 20th percentile. In this particular case, for our data set that we have, that 20th percentile is 6.18. So indeed, Lincoln would satisfy those particular conditions.